We're continuing with chapter 22, and we're actually going to finish it up. And we're going to focus on hypothesis tests for two proportions. So we're going to start by putting everybody into the pool. Unfortunately, that does not mean we're having a pool party. Looking at hypothesis tests. So the typical hypothesis test for the difference in two proportions is the one of no difference. What that means is that our first assumption is that there would be no difference between the two groups. So remember that null means nothing interesting, nothing exciting is happening. So if there's no difference, well, that's kind of boring. So that's our null hypothesis, is that the two groups, or two proportions, would be the same. So in symbols, our null hypothesis is P1 minus P2, which is equal to 0. That is going to be your null hypothesis every single time. So whenever you have to write a null hypothesis, it's always that. Since we are hypothesizing that there is no difference between two proportions, that means that the standard deviations for each proportion would end up being the same. Since this is the case, we combine them, or we're going to pool them together. So that's where the pool is coming from. Again, not a pool party. So by pooling them, we combine the counts to get one overall proportion. So the pooled proportion is calculated as p hat pooled is equal to the successes from your first group plus the successes from your second group divided by the sample size from each group added together, where your success for the first group would be your sample size of the first group times the sample proportion of the first group, and the number of successes in the second group is your sample size from the second group times the sample proportion from the second group. If the numbers of successes are not whole numbers, then you're going to round them first. This would be the only time you should ever round values in the middle of a calculation. Otherwise, you should always just keep extending it out and then round at the very end. But in this particular case, you need to have whole numbers for your successes. When we put this pooled value into the formula, substituting it for both sample proportions in the standard error formula, we end up with that our standard error pooled, so we always state that it's a pooled standard error, would be our p hat pooled, so our pooled p hat value times our pooled q hat value divided by the sample size of our first group, plus the p hat pooled times q hat pooled divided by the sample size from our second group. So we still have two groups and we have to add them together, but we use the pooled value because we are assuming that there's no difference between the two groups, and if there's no difference, they have the same proportion. So the proportion between the two groups should be the same, which is why we pool them together. However, they still are coming from two different groups, so we may have two different sample sizes, so we have to take that into account. Unlike previous hypothesis testing situations, the null hypothesis doesn't provide a standard deviation. So we'll have to use a standard error, which is why we're using the SE instead of the SD. So a two-proportion z-test. So that's what we're really trying to talk about today. The conditions for a two-proportion z-test are the same as for a two-proportion z interval. So we still have random, 10%, success fail, but we have to check the success fail for both groups, and then we also have that the two groups have to be independent of each other. When we are testing a hypothesis, once again, your null hypothesis is always going to be that the first group minus the second group is equal to 0, or equivalently that P1 is equal to P2. So your two proportions are equal, or the difference between the two proportions is 0. Either way is completely acceptable. Continuing to look at two-proportion z-test, we use the pooled value to estimate the standard error. So once again, our standard error is SE pooled is the square root of our p hat pooled value times the q hat pooled value divided by the sample size from the first sample plus our p hat pooled value times our q hat pooled value divided by the sample size of the second sample. Which means when we find our test statistic, and by test statistic they mean a z-score here, we calculate that as we find the difference between the actual proportion between our two groups, so p hat 1 minus p hat 2, and then we always subtract 0 because that's our null hypothesis, divided by the standard error of the pooled values. When the conditions are met, and the null hypothesis is true, this statistic follows the normal model, so we can use that normal model to obtain a p-value. So again, we're calculating a p-value just like we did before, based off of a z-score. So let's look at an example. Will I snore when I'm 64? Get it, we rhyme. The National Sleep Foundation asked a random sample of 995 U.S. adults questions about their sleep habits. What they found out is that of 184 people under the age of 30, 26% reported that they snore. Of the 811 people over 30, 39% reported that they snore. What we want to know is there really a difference, or is it due to only natural sampling variability? So is there a difference between age on if you snore or not, or do we expect to see these differences based off of natural sampling variability? So we have to do a 2-proportion z-test to determine this. Again, when we are doing a hypothesis test, we still have to run through the 4 steps. We need to find our null and alternative hypotheses, state what test we're doing and check our assumptions and conditions, perform the mechanics where we calculate our pooled values, our z-score, and our p-value, and then we write a conclusion based off of our p-value, where we will either reject or fail to reject our null hypothesis. So starting with our hypotheses, the null hypothesis is that the 2 proportions are equal. So you're going to snore the same regardless of your age. So old people snore just as much as young people. Our alternative, they just want to know if there was a difference. So our alternative is 2-sided because P1 does not equal P2. Then we have to check our assumptions and conditions. The first one is random. So the respondents were randomly selected and should therefore be independent. That was stated. Then we have our 10% condition. The number of adults in each age group is less than 10% of the respective populations. So each group is less than 10% of their population. And then the independent groups. The 2 groups are independent because this sample was selected randomly, so there's no reason to believe that one would affect the other. And then our success-fail. So again, for success-fail, we have to check it for both groups. So the younger group had 46 successes and 136 failures. Both of those are greater than or equal to 10. For the older group, we had 318 successes and 493 failures, and again, both of those are greater than or equal to 10. The first thing we want to do when we're doing our mechanics is label everything. So I'm going to say that Y means under 30, and O means over 30. So that way I know when I'm looking at P hat Y, I'm talking about the group under 30, so that's 0.26. And then P hat O, I'm talking about the group over 30, and that's 0.39. So once we do that, we need to calculate our P hat pooled value. So our P hat pooled is equal to 48 successes from our first sample plus 317 from our second sample divided by 184 plus 811, which ends up equaling 0.367. Once we have our p-hat pooled, we can then calculate the standard error of our pooled value. So in this case, the standard error is going to be the square root of 0.367 times 0.633 divided by 184 plus 0.367 times 0.633 divided by 811, and this equals 0.0394. Once I have it labeled as what my P hat Y, P hat O is equal to, I know my pooled values, I know my standard error, I can then calculate my z-score. My z-score is calculated as P hat O minus P hat Y. Typically, I always like to make the larger proportion first if I can. Sometimes they specifically tell you so you can't, but if you can, that's what I would do. But that minus 0, because that's our null hypothesis, divided by the standard error of our pooled values. So this ends up equaling 0.39 minus 0.26 minus 0 all over the standard error of 0.0394. So this means that z equals 3.33. Now a standard deviation above 3 is surprising, but we still need to calculate our p-value. So our p-value, because our alternative is two-sided, it's going to be 2 times the probability that our z-score is greater than or equal to 3.33, which would equal 2 times 0.0004, which is 0.0008. From here, I can then go on and give my conclusion based off of my p-value. Now that we've calculated our p-value, we can write our conclusion. And our conclusion is always based off of our p-value. So the p-value of 0.0008 says that if there really were no difference in snoring rates between the two age groups, then the observed difference would occur only 0.08% of the time. So that is what our p-value is telling us. That is the definition of the p-value in this context. What this means for our situation and whether or not there actually is a difference, because this p-value is so small, we reject the null hypothesis. There is enough evidence to suggest that there is a difference in the rate of snoring in the two age groups. That is all I have for tonight. I hope you guys all had a great night, and I will see you tomorrow.